Okay, so we're looking at some different kinds of stoichiometry problems here, where instead of just going from grams to grams, we're actually looking at solutions. And a lot of this is tied to titration. So one thing that all of these have in common, I'm going to show you 3 steps that you can take. Whether or not you do them all in one long stoichiometry is up to you, but ultimately the 3 steps for any of these problems are as follows. First thing we always do is find moles of your known. There's going to be one substance that you know enough about to find moles of that substance. Okay? And then the second thing is going to be using stoichiometry, find the moles of the unknown. There's going to be one thing they're asking the question about, and that's what I call the unknown. And then the third thing is to find what you're looking for, find what you need. Now there's lots of ways to do this. You could do it as individual steps, or you could just do it through an entire one long dimensional analysis. So let's start with this one. I guess we'll do this one as dimensional analysis. How many mils of, so we're looking for mils, of 0.450 molar, moles per liter, of HCl are required to completely react with 2.50 grams of zinc. And in this problem, you're basically setting up a scenario, since you're going to stoich from reactant to reactant, where you're not going to have something in excess. You want to know exactly how much of each thing you need to react with each other. Okay? Looking at this, which is your known? Zinc. So we're going to find moles of known, and I'm just going to start my big old dimensional analysis. All right? So go into moles like we always do. For every 1 mole of zinc, I have 65.41 grams of zinc. Okay, so now I have moles of zinc. Now I'm going to do stoichiometry, and my arrow was the wrong direction. We're going this way. And we're going to find the moles of the unknown. So what is that ratio? 2 to 1. So for every 2 moles of HCl, I have 1 mole of Zn. Okay. And then I'm going to find what I'm looking for. I am looking for mils. But right now, there's a piece of information that can lead me to something close to mils. What is that? The molarity is what? Moles over liters. So how can I place that where moles of HCl will cancel? Exactly. 0.450 moles of HCl per 1 liter of HCl is my conversion there. Moles per liter. Y'all comfortable with that? The reason I'm putting the moles on the bottom is so those can cancel. That gives me liters, but what am I looking for? Mils. So for every 1 liter, I have 1,000 mils. So to 366, what is my answer? 170. And in order to make that, I can put a decimal, or I could put a bar on top. I could do this. And then the unit is mils. And that is my answer. Pretty easy, huh? Okay, this is all we're doing today. Kind of the same thing over and over with just different little things thrown in. The next says, calculate the molarity. Now, I'm going to make a change here because there's going to be contradictory information between this problem and the next problem if I don't do it. So I'm just going to make this hydrochloric acid to make our lives easier. We'll be talking about sulfuric acid, which is a diprotic acid, and how it ionizes later. I just don't want to go there right now. This is enough for you to handle at this point. So we're going to calculate the molarity of this stuff in a 20 mil sample, which is neutralized by 18.5 mils of 0.750 molar sodium hydroxide. This is the exact same titration you're going to be doing in the lab on Wednesday and Thursday. I'm going to give you a base that's standardized, and you're going to know its concentration. And I'm going to give you some acid and figure out what its concentration is. And so what I'm doing in terms of calcs, you can mimic this for your lab, and you can start on that pre-lab as soon as you can. In order to do anything, what do you think we need first? a balanced equation, okay? So we're mixing sodium hydroxide, which is our known, with HCl, and what are our two products? Water and, the smartboard's got some drag going on there. Everything is slow today on the net. Okay, strong acid, strong base. If you want to be fancy, which I think you can handle it, can we go ahead and just write maybe the net ionic for this? Strong acid, strong base. What's the net ionic equation? Hydronium plus, or hydrogen ion plus OH minus gives us water. Pretty much the same thing. When we're doing a titration, we care about the ratio of acid to base. And that's all we really care about. Okay? So I'm okay if the lab you do, but since it's a strong titration, I'm okay if you use this as your balanced equation. Not a problem for me. No issues with that. But anyway, I am looking for the molarity of this. I have a 20.0 mil sample, and it's neutralized by 18.50 mils of 0.750 molar standardized sodium hydroxide. How this works in your actual titration. If you notice, we're neutralizing a 20 mil sample of acid. In this particular case, and you can tell by the way it's worded, when you do your titration, you're going to have your sodium hydroxide in the burette, and that's in a burette that's a graduated piece of glassware that y'all saw in pre-AP. And then you've got your little beaker. We're not going to use an Erlenmeyer because you're going to have a pH sensor in there, so we're actually going to use a beaker. And in here is 20 mils of acid and some water in there. Okay, so you're going to titrate till you reach something called the equivalence point. At the equivalence point, it's assumed that the H plus moles is equal to the OH minus moles. At the equivalence point here, they're saying that when you titrated, you used 18.50 mils of this standard sodium hydroxide. So you titrated, you started up here at 0, you added, and you reached the equivalence point at, we're saying that this is 18.50. You stop the titration, you write down your volume, and then you do your calcs. So now we're done with our titration. We neutralized our 20 mil sample, and we're going to start with the calcs. This problem I'm going to do in 3 steps. I'm not going to do the dimensional analysis, and then you guys decide what you prefer. I'll do the dimensional analysis on the next one again. So step 1 is find moles of known. Which is our known? The NaOH. So how do I find moles from molarity and milliliters? Not divide by. Molarity is moles over, but we want moles, right? So multiply molarity times liters. In the spring, y'all are going to be fast at this. You're going to be doing problem after problem after problem where you have to find moles from molarity in liters. So all you do is multiply molarity times liters. So what is 0.750 times 0.0185? 0.0139 moles, and this is of our known of OH minus. Okay? Now we're going to do some stoich and go from moles of known to unknown. What's our ratio? 1 to 1. Equivalence point, number of moles of acid equals number of moles of base. So this is also equal to what? Moles of H plus. Y'all are quiet. Do you see that? It's a 1 to 1 ratio. For every 1 mole of this, we have 1 mole of this. 1 mole of that, 1 mole of that. And now, third step is find what you need. What do we need? The question is molarity. We want the molarity of the acid. That's moles of H plus over liters of solution. So I've got molarity is what I'm looking for. What's my moles of H plus? 0.0139. How much H plus did I have in my flask at the beginning of the titration? What was my sample size? 20 mils. that right? Yeah. Okay, so what is the molarity? 0.695 moles per liter, and that's the concentration of your acid. And that's how you do the calcs for the lab. The lab's going to be similar, except we're not going to use 0.75 molar sodium hydroxide. I can tell you that right now. It's probably going to be 0.1. And we're also not going to have a 20 mil sample in here. I believe it's a 10 mil. Okay? But the calcs are the same. So as you work on your pre-lab, start mimicking those calculations. Yes, Johnny. Yeah, and it's really not an assumption. It's just the net ionic formula. And because it's a 1-to-1 ratio, the moles of OH equals the moles of H+. So as long as you write, I can see your formula and I can see, if you write this, to me, I see what you're doing. Okay? Don't just write this and then say, oh, that's 0.0139 moles of H+. And I'm like, well, where'd you get that? I need to see the thought process. Okay? All right, let's go on to the next one. This one I'll do dimensional analysis, same type of problem. Again, because of this contradiction that we're going to run into between this problem and the last one, I'm going to change this one again. And we're going to say it's sodium hydroxide. So we're looking for grams of sodium hydroxide, NaOH. We want grams contained in a 25.0 ml solution if 16.52 mils of 0.850 molar HCl is required to completely neutralize the sample. So we're looking for the grams of NaOH we need. So we have NaCl plus H2O. So I'm going to do this dimensional analysis. We know that this is our known and this is our unknown. So one long dimensional analysis, first step is to always find moles of known. Looking at the information we're given, how can I find moles of known? I'll just give you a hint. This is moles per liter. I always like to start my dimensional analysis with the simpler of the possible numbers in terms of units. Moles per liter is a double unit. This mils is a single unit. I think I'm going to start with that. Okay, so 16.52 mils. I'm in mils, which is kind of an issue. I'm not going to be able to, deal with that when I want to multiply with the molarity. So what should I change this to? Liters. So for every 1 liter, I have 1,000 mils. So now I'm in liters. How do I get moles of known? That's my first step. Look at your molarity. 0.850 moles per liter. And this is of the HCl. So my liters cancel, and now I'm in moles of HCl. That's moles of known. How do I get to moles of unknown? Mole ratio, which is 1-to-1. So for every 1 mole of NaOH, I have 1 mole of HCl. Those cancel. Okay, now I am in moles of HCl. What am I looking for? Find what I need. For every 1 mole of NaOH, I have about 40.0 grams of NaOH. So let's go ahead and solve. 0.5617. So 0.562. We'll stick to 3 because of the molarity on the HCl. 0.562 grams of NaOH are required to exactly neutralize that much acid. What's the limiting reagent? And what's in excess? What? Neither. Why? Because we stoiched over to it, right? We have exactly the perfect amount to react with each other. Okay, I was trying to trick you. All right, let's do the next one. What mass of iron 3 hydroxide is produced? So we're producing ferric hydroxide. What's the subscript here? 3. When, so we're looking for mass, 35 mils of a 0.250 molar iron 3 nitrate is mixed with 55 mils of KOH. So those are my 2 reactants. What would my other product be? Because I got to balance this equation. Potassium nitrate. I need 3 nitrates, which means I need 3 potassiums, and that takes care of my hydroxides. So I am looking for, it says at the beginning, I have 35 mils of 0.250 molar of this, and I'm mixing it with 55 mils of 0.180 molar of that. I've got a stoich over to here, right? But what's my problem? Correct. You have to figure out which one is going to run out. We've got to find our limiting reagent and which one's in excess. So to do that, I always find what? Moles of each. So this is, again, where you're going to get quick. You're going to quickly remember that to get moles from volume and molarity, you multiply them. Molarity is equal to moles over liters. So 0.250 times 0.035 is what? Okay. And this one is 0.055 times 0.180. 990. Okay. Now to figure out which one runs out, for every one of these we need 3 of these. So we divide, remember, quick by that coefficient just to see which one runs out. These are still moles. I'm not going to touch that. But look, which one runs out? The KOH, because this ends up being a 0.03 after the division. So this one runs out. That makes this one in excess. That makes this our limiting reagent. So I'm going to do stoichiometry from the limiting reagent to my ferric hydroxide. Okay. Starting with, are you okay if I start with these moles here? I think it would make the problem faster than having to go back and find moles again, because you already did it. 0.0099 moles of KOH. Stoiching over, find the moles of the unknown. So for every 3 moles of KOH on the bottom, I have 1 mole of ferric hydroxide up top. And then how do I get to what I'm looking for? Molar mass. So for every 1 mole, what do y'all get? What was your molar mass? 106.88. And then you said 0.353? 3. Can I get a second on that? Everyone agree with that? I just want to make sure it's good for video here, make sure our numbers are right. Yes. All right, done. That's good. We're going to do one more problem. But do you see how these are all similar? The same thing over and over and over again. The trick is you got to have that balanced equation, identify your known and unknown, and work from known to unknown. Last problem. Let's see who can figure this one out. It says if 25 mils of 0.625 HBr is mixed with 42 mils of 0.352 NaOH, will the resulting solution be acidic or basic? What are my products of this reaction? Water and sodium bromide. So again, if you really want to think of it, there's our net ionic. What do I have to do here? Yes, Philip. Very, very nice. Very well said. Find the limiting reagent. All the limiting reagent is going to be used up, right? So whatever's then in excess is going to be floating around in the solution, and that's going to contribute to the pH of the solution. So let's go ahead and do that. We know we have 25 mils of 0.625 molar of this, and we have 42 mils of 0.352 molar of that. We're going to then multiply, again, to get the moles, we multiply volume in liters, 0.025 times 0.625. What do we get? If you want to do millimoles, you can. If you just multiply those two numbers together, you get millimoles, and you can do the same kind of work if you want. My only hesitation in doing that is when we get to titration problems, the millimoles will have to be unconverted, which people tend to forget. So half of one, half a dozen, whoa, 6 of one, half dozen of the other. That's what I was trying to say. And what is this one? All right. The ratio, these are balanced, this equation's balanced, so it's a 1-to-1. So which one is used up and which one's in excess? This is in excess. This is your limiting reagent. So this is going to, or limiting reactant, all of this is going to go over, leaving us with extra acid. So this is what type of solution? Acidic. I like writing big on the board. Acidic because excess of acid. All right, so work on that pre-lab. Try to get that started so you can ask me questions tomorrow, okay?